All right, getting your fill of that data quality and error stuff yet? Last time you got a fill of those errors that maybe you can quantify, those attribute and positional errors. If they're categorical data, you can use an error matrix. If they're numeric data, you can use root mean square to calculate or estimate the errors. So now I'm going to go on and talk about topological error. And I haven't talked about topology yet, but topology is kind of a special thing that involves relations between spatial objects, okay? And topological properties are properties that aren't affected by, let's call it a stretching or a compressing or a bending of your surface. So you can think of it as a rubber sheet. When you stretch it or compress it, the topology remains the same. So in GIS, what does that mean? It's how points, lines, and polygons relate to each other spatially. When you create your data or when you're editing data, this is especially important because suppose you have a road network where you want a road to connect to another road like this shows here. If you draw one road extending over the other road, you're going to have this thing called a dangle or an overshoot where one road is actually overshooting what it should be. Topologically, you could enforce a rule that says those lines must connect. Suppose you have a polygon that you drew and you didn't draw it quite properly and you didn't close the polygon. Remember, that's essential for a polygon to be a polygon. It has to be closed, otherwise it's just a line. If you were enforcing topological rules, you might be able to say all polygons must be closed. Just like you have overshoot, you can have undershoot, and here you see this term called fuzzy tolerance. So the GIS, if you tell it to enforce topological rules, is going to be able to say all lines must connect. And if a line doesn't connect and it's within this fuzzy tolerance, you can tell the GIS to go ahead and connect it. Same thing with unclosed polygons. If it's within a certain tolerance, you can have the GIS go ahead and close that polygon. So when you're editing data, a good way to prevent creating errors in your data is to enforce topology. This is another one that is associated with polygons. And let's say you're drawing a polygon for Idaho and a polygon for Washington, and you think you have those two polygons where they share a border lined up really well. Well, if you zoom in really close, you're going to find that the Washington polygon and the Idaho polygon don't mesh. So there's going to be places where Idaho and Washington overlap, and there's going to be places where there is no state, no Idaho or Washington. So that's obviously going to be a topological error. So when you have polygons that are close to each other but not exactly adjacent, you can again use this fuzzy tolerance, and by enforcing that, you're going to be able to force adjacent polygons to be adjacent. So we have connectedness and we have adjacency. There's another concept associated with topology that's called enclosure. And you can imagine having all the cities in Idaho and a polygon that's the boundary of Idaho. You can enforce topology to say all cities in Idaho must be enclosed by the boundary of Idaho. And then if you tried to draw a city that was outside of the boundary of Idaho, topological rules would say, no, you can't do that. What's temporal error? Well, of course, it's error having to do with time, so it's about the when that's associated with the data. So, are the data up to date? Also, are the data consistent logically in terms of when they were collected? If you collected some data in the winter and some data in the spring, then some of the attributes associated with that data would be expected to be different. But if you don't know when the data were collected, you're going to have errors in one or the other. And again, these are all going to be things that get reported in the metadata. So if you have good metadata, you're going to be able to tell where the errors might be and be able to work around those errors, or to even prohibit yourself from doing an analysis using data that's got too much error in it. Once you kind of have an idea of what this error is, you can actually make maps that visualize the error. This comes from your text. This might be a positional error map that shows when you went out and did your field checking, where the errors were and in what direction they were. And so when you see error arrows that point in a consistent direction or are a consistent length, then you might know that there's something going on in terms of maybe the instruments you used to collect the data, or maybe the projection you used or a transformation you used that's putting a consistent bias in the data so that all of your data is in error by kind of the same amount. If things are kind of random, then what you're seeing is when you measure it every time there's going to be some random error in that data, and so you should expect that, and that's just part of the way that data collection works and what modeling and representation of reality is about. So here's another visualization you might be able to use for polygons. So let's say you say it's forest or it's not forest. Well, on the edges of the forest you're not sure. Is it really forest or is it maybe transition to cropland? So it's kind of hard to tell exactly where the boundary between forest and cropland is. So if you had a good error analysis, you might be able to say, well, I'm pretty sure that the forest in this darker color is really forest. This other area may be transition, it might be mostly forest, it might be mostly cropland, so I'm pretty much 95% sure that it's forest, but it could be a large percentage of cropland in there. So if you have some type of quantification or an idea of what type of error you're experiencing, you can visualize that error and provide that information to the person who's going to use your data so they'll know whether or not the data is going to work for them. Error propagation. This is the garbage in, garbage out thing. So assume we have a data set that says what kind of crop we have, corn. We have another data set that says what type of soil we're growing that corn on. We got some sand and we got some clay. We have a third one that shows where our irrigation system is. So we've got 3 data sets, and really we want to know where we're growing corn in the sand in an irrigated area. So when we overlay all that data, which I'll talk about in a couple of weeks, you get this output which says this piece here is corn in the sand and it's irrigated. This piece down here is also corn and it's in the clay and it's dry land. So that all looks good, but if you've got a really good crop coverage data set and you've got a really good soil texture data set, but something's wrong with your irrigation data set, your entire map is going to be wrong. Garbage in, garbage out, the weak link of the chain. So if you were to do this correctly, possibly this would be the way that the irrigated, non-irrigated data set looks, and you would get a completely different map. So one data set that has error is going to propagate through into the output. Numerically, that also applies. So let's say we have a true A equal to 100 as an example. True B equal to 100. So we know that the real values, or as close as we can measure them when we go out in the field, are 100 for A and B. If we measure those two and we multiply them by each other, we say, well, if A is true and B is true, we're going to multiply A by B, we get 10,000. Now let's say A is off by 10%, roughly. And let's say B is off by 10%. Now when we have inaccurate A's and B's, and somehow we need to multiply A by B as part of our GIS, we're going to have an A times B that's not 10% but 21% in error. So errors propagate numerically and just physically. Errors propagate through the data. So bad data in equals bad data out. Next time I'm going to talk about 2 other things that are considered errors, but they're really not errors so much as they are improper thinking about the way the data is being communicated or the information is being communicated to you, or improper thinking about the way that you make your map and the message that you're trying to send.